Welcome to the next lecture of Mechanics of Material. This is Salman, Assistant Professor, ISL Engineering College. In last class, we discussed about strain energy. That is nothing but the energy stored in a body within elastic limit. That we have studied by various types of load. That is gradual load, sudden load, and by impacting load. And we have seen a problem on gradual loads and sudden loads. Today's lecture, we are going to discuss about the other types of problems and strain energy. So let us discuss the first problem. So the very first problem is a steel bar of meters long is 500 mm cube in cross section uh, is given cross sectional area. What is the instantaneous stress produced in a bar due to axial pull when its extensions was observed to be 1.5 meters or 1.5 mm. Also find the magnitude of the axial pull when E is equal to 200 gigapascals. So when we say instantaneous, you have always go to you have always solve the problem based upon sudden loading. Okay, instantaneous means to that particular instant. Okay, so when we have to use this, we have to always calculate the by using sudden loads. Okay, instantaneously basing upon at that instant how the load is going to be at, either it is a sudden load. If it is a gradual, we will never ask instantaneous loads. Okay, so the given data has been taken here. Length 3 meters that we have converted into millimeters. Area is given as it is. So area of what we say elongation is given 1.5 mm. Young's modulus is given. We know that delta L is equal to sigma into L by E, where this delta L is given as instantaneous, so the stress will also be instantaneous. So basing on that, we can able to get the value of sigma instantaneous, and we have find the value of it. Okay, so this is a very small problem. We also know that when instantaneous stress is induced in it, it will produce the gradual induced load as about twice of the gradual loading. So by using this instantaneous load, we are going to find the gradual loading, and with that we can able to find the value of the load which is acting on the material. So they are asking instantaneous stress induced as well as find the magnitude of the axial pull. So when the instantaneous stress is asked, so this is the instantaneous stress. So with respect to instantaneous stress and the gradual loads, what is the difference is nothing but the instantaneous stress is generated when load suddenly falls on it. But whereas gradual loads are what is the load is nothing but when you are applying the load on a material, that is nothing but the load acting on it. So we know the relationship between the instantaneous load and the gradual load. Basing on that, we can able to identify the value of load. Okay, so we have done both this. So the next problem is a load of 10 kilonewton here falls freely through a height. Whenever the height comes, you have to go for an impact loading. Okay, a 12.5 millimeter onto a collar attached to the end of the vertical rod, which is a 50 mm diameter. Diameter is given, length is given. So the upper end being fixed so to the ceiling. What is the maximum stress induced in the bar? Take E for the rod is 120 gigapascals. So let us take the data which is given as given data should be equal to 10 kilonewtons. Kilo is nothing but 10 to the power of 3. Load falling from a height of 12.5 mm. So this is given in mm. So no need to change. Next, length is given. So length is equal to 3 meters. We have to convert into mm. So we are taking that. Young's modulus is given. Young's modulus E is equal to 120 gigapascal. Giga can be written as 10 to the power of 3 Newton per mm square. Diameter is given 50 mm. We know that whenever the load is falling from a particular height, that is nothing but impact loading is being done. We know that the stress induced will be sigma is equal to P by A of 1 plus under root of 1 plus 2 EAH by PL. So this is the formula you have to remember. So in this, all the data is given, area is given, E is given, H is given, P is given, L is given. So try to substitute all the values. What is area here is nothing but, since this is a rod which is having diameter, obviously the area will be equal to pi by 4 d square. You have to always consider the area of cross section because the stress will be acting on the area of cross section itself. So if you take this 2 into 120, here you can see that area is equal to 1963. I have written 1963. Next, E is given 120 gigapascal, 120 to 10 to the power of 3. height is there 12.5 divided by PL. This is my load 10 into 10 to the power of 3. This is my length. So I have solved, tried to solve this all values first in your calculator. So you will get a value like this. So add these two values, you are going to get now 197.349. Once you get this value, find the square root of this. So after finding the square root, you can find the values by doing plus and minus, because you are having here plus or minus. So sigma max is nothing but, when they ask sigma max, you have to do plus. When they ask sigma minimum, you have to do minus. Clear? I hope you are clear with this. So they are asking here sigma max, so have find the value of sigma max. The next topic we are going to discuss is, as we have seen how the loads are going to be acting on varying sections, similarly the strain energy will also be having an impact on varying sections. So as we have discussed in the previous lecture, that total deflection in a varying section will be is equal to delta L plus delta total transfer deformation is equal to delta L1 plus delta L2. Now the strain energy is basing upon the strain. The strain energy itself is nothing but based upon the strain, how much amount of material is getting to strain. Because of that, the strain energy is produced. So we have already known this. Delta L is equal to, let me take this ink. So delta L total is equal to delta L1 plus. So the strain energy is also nothing but, since the name itself is strain energy, we can even take it as UA plus UV. That is nothing but delta L total is equal to. Okay. So maybe coming across a bars of varying section where we are going to find this. I hope I am clear with this. Couldn't able to draw here, not a problem. So if you are having n number of varying sections, you have to take U is equal to U1 plus U2 plus U3 plus U4 in that way. Okay. So you have to calculate the varying sections. So let us take one problem. A non-uniformic tension bar. So tensional force is acting on it. 5 meter long is made up to 2 parts as shown in the figure. So it has been made 2 parts out of, this is 3 meters, this is 2 meters. 3 plus 2 is 5. Okay. And the area of cross sections is given. So obviously this will undergo a deformation like delta L1. So this will undergo the deformation like delta L2. So since they are going on various types of deformations, obviously the stress or the strain energy stored in it will be different. Example I can give. You take a spring. If you compress the spring to a small extent, that much amount of energy is stored. If you are compressing the spring by taking 2 hands, so it will store more amount of energy. Similarly, how much amount of strain the material undergoes, that much amount of energy will be stored in the object. So here they are asking, find the total strain energy. U total you have to find, so you have to calculate the strain energy for the section 1 and you have to calculate the strain energy for section 2. So they have given the loads for you, so you have to calculate the sigma. You know the strain energy formula. Strain energy UA is equal to, you can take the first section as UA and section B as UB. We know that section A is equal to, UA is equal to sigma square by 2E into volume, that is nothing but area into length. So for that we have to calculate, we know this formula, sigma square by 2E into volume. So what is sigma? First we have to identify. How we will calculate? They have given you the load. This load is acting on which area? This cross sectional area. So what is this cross sectional area? They have already given 1000. So with that I can able to calculate the sigma 1 here. So sigma 1 2E, they might have given the value of E here. E value they have given properly 200 gigapascals. So I will substitute here. Next is V1. What is V1? Is nothing but volume of this section 1. Volume of this section 1. I am trying to draw this. This is a section 1. So what is volume? Volume is nothing but area into length. Area is 1000. Okay. Next is you have to take the section 2. So when I take section 2, the load is acting like this. Why we are taking this section is, we have already discussed in the if a common load is acting, then you might split the varying sections like this: first half, second half. Okay. So the load, the tension force is coming from here. This force is acting from here. Similarly, this force is acting from here. This force is acting from here. The directions, if you take this and this, so this and this, and this. Okay, we have already discussed this. These two are equal and opposite, so they will nullify. That is the reason here there is no extra loading, only the load is this, at this section, at this section, at this section, at this section. These two sections at the center will be nullified. That we have already known. So we have already done this in the first in the initial cases. So sigma 2 we are going to calculate, that is P2 by A2. So P2 is 70 into 10 to the power of 5, because the same load is acting across the whole material. Area is 2000, then we can able to identify the sigma 2 as 35 Newton per mm square. So once you find the sigma value, you can calculate the value of U2, that is sigma square by 2E into volume. So sigma square is nothing but how much? 35 square divided by 2E. Since E is same, 200 into 10 to the power of 3. The volume of the material is 2000 into 2000. So you are going to get the value of U2 as 12.5. So 12.25 kilonewton millimeter. So U total is nothing but now you have to add both the values, U1 plus U2, U1 plus U2. So this is in this way you have to calculate for a varying sections. So the next problem, this is very important problem. This has been asked in most of the question papers. Try to understand this problem very clearly. So the two similar rods of bar round bars A and B. So this is my bar A. Okay. So here I am drawing, this is my bar A and this is my bar B. So we are having two bars. So in both the bars, if you see, so they have given some data as shown in the figure. Each are 300 meters length. The total length of both the bars is 300, 100, 200. So but in this varying section, the first section in this is smaller, the second section is, the bigger section is longer. But whereas in this, the smaller section is longer and the bigger section is lesser. But both the bars are of same material, same type, and same length, not same type, same length. Okay, and they have produced a maximum stress of 100 megapascals. So it can take maximum sigma as 100 megapascals. Find the maximum stress produced by the same blow on the bar B. So if this material is also having the same maximum stress produced by the same blow on the bar B, if the bar B is also stressed to 100 megapascal, determine the ratios of energies stored by both the bars. So first what you have to do is you have to calculate the total strain energy of the varying section UA. Okay, how to calculate this UA is nothing but UA1 plus UA2, because this is my section 1, this is my section 2, because the area is varying. So UA total is equal to UA1 plus UA2. Similarly here UB1 plus UB2, UB1 plus UB2. So here understand the question properly, which is produced. So the bar A receives an axial blow which produces a maximum stress of 100 megapascal. Find the maximum stress produced by the same blow on the bar B. Okay, if the bar B is also subjected to 100 megapascal, determine the. So they are trying to confuse you in a small way. So the only thing you have to do is you have to understand that this bar, this total bar, for example, what is the diameter of this? This diameter is 20 mm. What is the diameter of this? Diameter is 40 mm. We know that what is the relationship between the diameter and the sigma? Sigma and diameter are reciprocal to one another, because sigma is equal to P by pi by 4 d square. P by pi by 4 d square. Whichever the diameter is lesser, that will have the maximum sigma. Whichever the diameter is having lesser, that will have less sigma. So in this what we have to do, so they have given you the sigma as 100 megapascal, for which you are taking, if you see the previous problem, because of the areas they are having different sigma values. Here it is 70, here it is 35. So how to take 100 they have given, for which part we have to take 100, either for A part, so this for the section 1 or for section 2. How to identify? But they are saying that this is the maximum value, both should not cross the value, that is 100. So what we are trying to do is the area whichever is smaller, that will take the maximum load. That is the reason sigma A1 is equal to 100. sigma A1 is equal to 100. Now since both the areas are having a relationship, that is sigma A1 is equal to, we can take out the relationship between these two, because when they are saying that this is the maximum stress, the material will be subjected to same kind of loading, okay, because it is the same material and it is made up of varying the cross sections, because it is same material which is only changed in the dimensions of the material, so obviously it will be subjected to same loading. So when the load is constant, this is constant, this is a sigma is inversely proportional to diameter, so sigma A1 by sigma A2 is equal to dA2 square by dA1 square. So with this, sigma A1 we can take it as 100, sigma D2 we know it is 40 square, sigma D1 is 20 square. With that you can able to identify the sigma of second section, that is nothing but part 2 of A. So with that we have identified that sigma A2 is equal to 25 Newton per mm square, but whereas for sigma A1 is, this is nothing but for part 1 is 100 Newton per mm square. So basing on that, we are going to calculate the overall energy for the part A, that is UA is equal to UA1 plus UA2, that is sigma square by 2E into VA1 plus sigma square by 2E into VA2. So substitute sigma A square is equal to 100. E value they have given in the problem. You can check out the problem. They have given the E value as, sorry, they have not given the E value. So since both are same materials, so whichever is unknown you keep as it is. So I am keeping, pardon, sorry, let me check E value they might have given. I think I have not taken down here, but they have given the value of E. So okay, they might have given the value of E, so I have not written down here in the question. So follow this. They will be giving the value of E. So I am substituting. I am going to get the value of U as 2356.188 Newton per x. So I hope everyone is understanding this to this extent. Only thing you might be confused with the value of E, that I might have forgot to written down. Now we are trying to solve for section B. Similarly, the section B is also, they are saying that it can only take the maximum blow of 100 Newton per mm square or 100 megapascals. They are clearly saying 100 megapascals. So which part it will take, second part or first part? Obviously the first part. Why? Means this is having the small diameter. We have already studied that the diameter which is less, it will take more, that is nothing but maximum. So sigma B1 divided by sigma B2 is equal to dB2 square by dB1 square. So here also you are going to get the dB2 as 25 Newton per mm square. Only difference in this is nothing but the volume is going to be changed. Initially the volume was different, here the volume will be different. So volume is nothing pi by 4 d square into length. Initially the small diameter length is 100 mm itself, here it is 200 mm. Okay, so with that, yes, 200 mm. So with that we can able to solve the problem. I hope you are clear with this. You have to take down all the values same. Only thing is volume B1 will be changed, volume B2 will be changed, and you have got the value of 3534.28 mm. Someone may having a doubt, sir, they have not given the E value, so I will not write the E value, you might have taken by mistakenly. Okay, no problem, you keep the E value as it is here. So this E value will come like this, and you will get the value. Instead of getting 3534, you will get some value and you will have a value, you will have E below it. Okay, similarly for the above also you will be having UA by E, that is nothing but this value divided by E. Now if you take the ratio, this E will obviously will get cancelled. They are asking you to find the ratio itself, ratio of strain energy for the part B and part A. So they wanted to explain that if the areas has been changed, the cross sectional area has been changed. So if the cross sectional area which is smaller, if it is changed, if the length of it is increased, then it is able to store lot of energy, more amount of energy, which is almost like 1.5 times. If you see the two sections, initial section is having small thickness, but whereas this length is bigger one, this length was bigger one. This is my A section, but whereas B section they have made the small length bigger and this huge length, huge diameter they have made smaller. So among these two, what they have observed is this will absorb more amount of energy compared to that of this. A section will be absorbing less energy, but whereas B section will be absorbing more energy since it is of small thickness and diameter is lesser. Okay, this is what they wanted to explain to you. Clear? So with this, the strain energy topic is ended. So the next topic in our syllabus is the principal stresses. What is this principal stresses? Is nothing but when you are trying to solve one problem, you will be coming across a normal strain as well as the shear strain. We have already discussed what is a normal force, what is a shear force. I have explained you. So what is normal force? If there is some object like this, if the force is acting perpendicular to the surface, either it is a tangential or either it is a tensile or compressive, both the forces are normal forces. If the force is acting parallel to the surface, then we call it as a tangential force or shear force. Tangential force or shear force. Now what is this principal plane? Is nothing but the plane in which there is no shear strain. There is no shear strain, only normal force is acting on it. If only normal force will act on a plane, what happened to that plane? That plane will either expand or that plane will either contract. For example, you are having a plane like this. Okay, now you are only acting the normal force on it. You are having only. Now what happened to this? Either it will increase the length basing upon the type of load. If it is a tension, it will increase its length. If it is compression, it will decrease its length. So that type of planes are called as principal planes. So you may ask me, sir, is it every time horizontal and vertical? No, it can be inclined planes also, that we generally called as oblique plane. If there is a material like this, if you want to find a particular plane on which there is a how the stresses are going to act, this plane is called as oblique plane, which is making an angle theta with either horizontal or vertical. So basing on the type of problem, we are going to solve this. So principal stresses. So what is principal stress? On a principal plane, the magnitude or the amount of direct stress acting is called as principal stress. The sigma value which is acting on a plane which is having no shear is called as principal stresses. So this principal stresses we can identify by two methods. One is analytical method, another is graphical method. Analytical method is nothing but by doing some mathematical solving. That is nothing but by taking out the relationship between angles, this, that, and we will try to solve that. But whereas graphical method is we draw some type of graphs, and basing on the graph measurements, we are going to find that. Okay. Analytical is purely mathematical. So in this, we have to identify an analytical method. We have some sign conventions. All the tensile stresses and strains are positive, whereas compressives are negative. We have already studied this in the first initial sections itself. A tensile force will be always considered as positive, and the compressive will be taken as negative. Similarly, the shear stress which tries to rotate in clockwise is positive, but whereas anti-clockwise is negative. So in this we have four different cases. One is direct stress, another is two direct stresses. One is along x-axis, y-axis. Another is direct stress with what we say shear stress, and the direct stress, two direct stresses again with a shear stress. So among these four cases, I will try to solve with one or two cases today. Then we will try to go for the other sections. Okay. So this all comes under your first unit. Your first unit is one of the longest units. So consider an element in a rectangular shape with a thickness, unit thickness. What does this mean? Nothing but this is a rectangular section. It is having a cross section internally like this. So it is having a cross section. If you want to draw it properly, so the cross section of this is like this. Sorry. So this is my rectangular section which is having, clear? So this length I am considering this unit thickness. Unit means 1, which is pulled by a tensile force along xx direction, So an oblique plane is at an angle AB dash, which is an axis which is at an angle of theta degrees with the horizontal. Okay, so this is actually called as oblique plane. Okay, because of this this will try to expand. So while the expansion, you might be observing there are few planes. So if you have studied in metallurgy and material sciences, there will be dislocation of planes. So because of dislocation of planes, you may come across this kind of plane also. So that is the reason we are studying about the oblique plane. So let us consider. So this stress is so this normal force is acting on this. So this normal force, generally the load is acting. We does not apply the directly stress. We generally apply the load. Because of the load, this stress will be coming into picture. So what I am trying to do is I am trying to take this section A, B, B dash separately. I have drawn this section. When this normal load is acting on this load will be acting on this plane in this way. Okay, clear? So this force will be having two components, that is nothing but one will be the perpendicular to the surface, another is along the surface. The perpendicular to the surface type of force is called stress is called as normal stress, and this along the surface is called as shear stress. These two will have a resultant like this, which is nothing but sigma. You can consider that is nothing but sigma r. That is nothing but sigma r. So our whole concept rotates about this normal stress and shear stress. So I have separately drawn this figure now on which these forces are acting. So what we have to do, this is an purely the normal force act on this normal to the surface, shear force act on this surface. Now this is the only load we are applying. These are the inherent. So this I have to resolve about these forces, about the normal forces. So what I will try to do is I will draw a force with for example, if you see this is the horizontal line, this is the tangential line, and this line and this line are parallel. So I will draw a line which is parallel to this, like this and this are parallel. Now similarly to this extension line, again I will draw line like this. Now what is this angle? Obviously this is theta. Why it is theta? Because horizontal and tangential, this line, horizontal and this line. So I will try to highlight by using another color. Okay, horizontal and this and horizontal is similar to this and this. So whatever is the angle subtended here, the same angle will be subtended here. That is nothing but basing upon the similar triangle technique. So this is the technique. Now I have to identify the direction of this. So for identifying the direction, let us take this. This is the arrow mark of sigma. This is the arrow mark of sigma. Your sigma is going from left to right. Your sigma is going from left to right. So the components of it. So what is your initial position? This. What is your final position? This. So you have an option of going this way. Okay, this is my this way. Another is from here a perpendicular should be drawn towards this. So these are the two components, one this component, other this component. So this I will try to highlight here again using a different color. So this is similar to that of this value, and this is similar to that of this value. So that is the reason I am taking this direction as above and this direction is downward. So I am taking as downward direction, that I have drawn here. Above direction, this is downward. Now since this theta is next to this angle, so this is obviously called as cos theta. So this is obviously called as cos theta. Similarly this side is going down and it is this side and this side are parallel. So this is nothing but sigma sin theta. This is in the direction of sigma, but whereas this is in the direction of tau, and this is in the direction of sigma n. This is in the direction of sigma n. Okay, now when we are trying to resolve the forces, you should be very much clear that you should only resolve the forces parallel to these two forces. You should not go along the x-axis and y-axis. You should only try to solve the problem according to this. You might have solved this in friction. If you are having a wedge like this, if there is a object which is sliding, so if you have a weight like this, you will try to resolve the weight along this. Okay, similarly here you have to resolve along the wedge itself, because this is your plane on which the forces are acting now. Okay, so now you are clear, I hope. Okay, I will try to erase all these things so that you can able to understand clearly. I have drawn with pencils much clearly. So if you see, sigma n and sigma sin theta are opposite to one another. Tau and sigma cos theta are opposite to one another. So you cannot equilibrium the stresses. You can only equilibrium with respect to areas. What is the relationship between the stress and area? We know that sigma is equal to P by A. Sigma is equal to P divided by A. That is nothing but load upon area. But whereas force P is equal to, or load P is equal to sigma into A, where sigma is equal to, sorry, P is equal to sigma into A, correct? So we have to multiply with areas. Clear? Now see, this sigma n is acting on the area A, B, and along with that a unit thickness which is like this, So that is the reason we take the this force which is acting normally nothing but sigma n into AB dash into L. So AB dash is this length, this is like a rectangle now, this length into this, AB into 1. Similarly, this section, if you see, this force sigma cos theta is acting on this area, that is nothing but sigma B into, here again it will be having an area inside which is nothing but called as 1. We consider it as 1 again. We have already discussed that the thickness is 1. So sigma n into, so now we are resolving the forces which are in normal direction. Here I am written the forces along sigma n direction, sigma n into AB into 1, whereas this is sigma sin theta into 1, because this and this are in same direction, this and this are in same direction, so we are equating. But whereas they are equal and whereas they are opposite to one another, so I have equated directly. If you want to write as an equation, when it is like that, if it is positive, this will be minus. That should be equilibrium, means upside force is equal to downside force. So we are trying to equate this. So with that, you can able to calculate the value of normal stress. We can able to calculate the value of normal stress, that is sigma n is equal to sigma sin theta into AB by AB dash, AB by AB dash. After doing this, you don't know what is AB and what is AB dash. So what you have to do is, you will simply do one calculation, that is nothing but you have a triangle, so or else I will try to keep as it is. Okay, so we will try to use this. Here we have another triangle, we know this A, B and B dash, A, B and B dash. Okay, A, B, B dash we have, and we know that this is angle theta. So here we have a relationship of AB and AB dash. What is AB? This is my AB, this is my AB dash, correct? AB and AB dash. We know that, sorry, this is AB dash, AB and AB dash. This is nothing but opposite side. This is your hypotenuse. You have relationship between opposite and hypotenuse. What is opposite and hypotenuse? Is nothing but sin theta. What is nothing but sin theta? So in the place of AB by AB dash, we can able to write sin theta. Here I have written from ABB triangle, sin theta is equal to AB by AB dash. Therefore we are taking sigma n is equal to sigma sin theta into sin theta, which is nothing but sigma sin square theta. And we have an identity, cos 2 theta is equal to 1 minus 2 sin square theta, which I am written as 1 minus cos 2 theta divided by 2. So now the equation of sigma n is equal to sigma by 2 of 1 minus cos 2 theta. Similarly, the forces which are along the tau direction, that we have to resolve. Which are in tau direction? This tau, and another is sigma cos theta. So I will try to highlight this force and this force now are in same direction. So I am trying to resolve that both are in opposite direction. Tau into AB into 1 is equal to sigma cos theta into AB into 1, because it is acting on the AB plane, this is acting on AB dash plane. So sigma into cos theta into AB by AB dash, this AB is coming this side, so this will become AB, so it will become into the denominator. So this will become AB by AB dash. Again go to this triangle, you will see that what is here it is like, yes, AB by AB dash. Again we have already found AB by AB dash is nothing but sine theta. So we have already substituted sine theta. So sigma cos theta sine theta you have. You might go to your identities. You have an identity sine 2 theta is equal to 2 sine theta cos theta. Sine theta cos theta is equal to sine 2 theta divided by 2. You have substituted that value. Tau is equal to sigma by 2 sine 2 theta. You have found now tau n and sigma n. Tau n and sigma n. So on this oblique plane you have found two forces. One is normal force, another is tangential force. That is, one is tau, another is sigma n, another is sigma n. So you have to find the resultant of these two. I am going to find the resultant. R is equal to under root of sigma n square plus tau square. So I hope with this we can solve stop, because you will be getting more confused after if I keep on teaching this. Thank you.